Welcome to this recording of my ESFSS 2025 presentation. I am Ruben Van Coile. I'm from Ghent University, and today we're going to talk about which test is the best. Now, imagine that you are responsible for evaluating a structure post-fire, and you are asked whether or not the structure is safe for continued use. Now, should you do any tests? And if so, which tests should you do? Or maybe you are a researcher and you are interested in characterizing the time to ignition of PMMA samples. Now your test setup is all very clear, but you don't know how many repeat tests you should do. And you don't want to do too many because then you're going to block the equipment for all of your colleagues. So how many repeat tests make any sense? Or maybe you're a fire engineer and you're working on the refurbishment of a shopping center. As part of the refurbishment, they're going to introduce CLT slabs, and you want, as part of your fire strategy, adopt a burnout resistance concept. Now, the only information you can reasonably get are standard fire resistance tests. So what can you learn from a standard fire resistance test for your burnout resistance, and does it make sense to have any repeat tests? Now, all of these questions, they are very different, but the approach to answer them is actually universal. And this is what I'm going to introduce next. What we are going to do is we're going to quantify the utility of doing a test or an experiment before actually doing it. The methodology is as follows. So first of all, you have to be clear about the context, really. Are you interested in time to ignition of PMMA samples, or are you interested in evaluating the safe continued use of a concrete structure post-fire? Then you need to be clear about your goals. So is it actually reducing uncertainty? Is it minimizing lifetime cost, or anything else? After that, you need to specify your experimental protocols. Now, what does that mean? That means you need to be clear about what different tests are actually possible to be executed. And you need to specify your parameters of interest. So these are the uncertain parameters of interest. That means that if you knew perfectly well the, let's say, single value for those parameters, then your problem was basically solved. So because of the uncertainty you have on these parameters, you might want to do tests and actually improve your assessment. For those uncertain parameters of interest, you look into existing databases, expert judgment, and so on, and you evaluate prior distributions. So a prior distribution, this is a probabilistic characterization of these parameters of interest. And then you need models. An experimental model, which maps those uncertain parameters of interest to what you will actually observe in your experiment, and a performance model, which maps those uncertain parameters of interest to what you are actually really interested in. And then you do a pre-posterior Bayesian analysis. Now, a pre-posterior Bayesian analysis is basically a fancy word to just say you're going to be honest in a mathematically rigorous way. So you already specified your prior distributions. You have been clear what you actually believe to be true, given all the information you have available, and you're going to mathematically take this uncertainty and then see what kind of things results you expect to see in your experimental protocol. And if you see those test outcomes, how it is now going to update your beliefs. You're going to define utility functions. Now, a utility function is just a mathematical characterization of this goal you have in mind. So for each possible test outcome which you get, you want to evaluate, okay, if I have this test outcome, that changes my evaluation this way. Now this changes whether or not I'm going to repair my concrete slab, for example, in the post-fire case, and that then changes how much it will actually have as a lifetime cost, for example. Now each test outcome you might have will be different, because you don't know upfront what will be the test outcome, so then you take an expected value. And this gives you then an expected utility for the overall test protocol. Now that's a lot to digest immediately, I realize. So we're going to go through all those steps in a slightly calmer way. And we're going to do this considering the example I've prepared specifically for this conference. And it's a very simplified case, or very simple case, where all the calculations can actually be done in Excel. So we have analytical solutions. So that means that everybody can, with 1 day, 2 days time, just recreate all the calculations here. And I refer to the conference proceedings for all the details. So first of all, let's sketch the problem. We're looking at student housing, and as part of the fire risk assessment, a very important parameter is the sprinkler success probability. And then the project team looks into British guidance documents, and they find a sprinkler effectiveness probability of 90% as expected value, but a lower value of 46% and upper value of 97%. Now, so this is very inconvenient, to say the least, and there is a lot of discussion in the project team. And as part of the discussion, they come up with a conclusion, really, and they say, like, well, actually, we can explain this 46% and this 97% by recognizing that there are really just two regimes of fire safety culture. We have a weak regime and we have a strong regime. So in the weak regime, basically, the sprinklers have been installed, but people don't really care about them too much. In the strong regime, proper maintenance, proper follow-up is being done. Now the client says, of course, that they are in the strong regime and they are willing to do some tests in some way to actually prove it. And two approaches or two test protocols are then put forward. One is to do 3 independent sprinkler tests in their different student housing facilities. And the other one is to go through all the different student housing and to check fire doors whether or not they're all properly closed. And we're going to do that 100 times. And why is that the last thing? Is because from the fire door closure, you can then see whether or not you're in the strong regime or the weak regime, and this will then update your belief on your sprinkler effectiveness actually. Details on that thing, again, in the proceedings. And the project team agrees that, okay, both test protocols sound reasonable in a way, and they're going to go for the test protocol which reduces the uncertainty on the sprinkler effectiveness the most. So, as I just said, 2 test protocols, but here I'm only going to show results for 1, 3 independent sprinkler tests. The parameter of interest, so we're going through the different steps here. Uncertain parameter of interest is our sprinkler success probability, and we don't need mapping models because what we are interested in is actually this sprinkler success probability, so we don't need to map that, and we are directly observing successes or failures when we do those sprinkler tests. The data we have for defining our priors is the data we have from the British guidance document, together with the consideration that there is a strong regime and a weak regime. So what do we do next? We define for both the strong regime and the weak regime a beta distribution. And we say if whether or not we are in the strong regime or in the weak regime, we're going to use a probability for that. So a probability W of being in the weak regime, and then the probability 1 minus W of being in the strong regime. So why these beta distributions? Well, first of all, the beta distribution is very flexible and it allows to basically calibrate it so that the different quantiles of those distributions align with the numbers we have from our data from our guidance document. And so we have this expected sprinkler effectiveness of 90%. Secondly, a beta distribution has analytical solutions for our Bayes analysis, which comes next. And this is actually common for researchers in general. It might seem that, well, isn't there a slightly different distribution which might be slightly better aligned or anything? Yeah, maybe, but you will increase the complexity of your calculations a lot, and you're not going to necessarily gain much there, especially if you take into account all the different assumptions which are done elsewhere in the analysis. So this is actually a comment regarding consistency of crudeness, really. If I plot these results, or these prior distributions, here you have the weak regime with the blue curve, here you have the strong regime with the orange curve, and the green curve, which has 2 bumps, right, 2 modes, is our mixture regime. This is probability density function, same data here in a cumulative density function. So now up to our pre-posterior Bayes analysis. So even before doing any sprinkler tests, we already know what we can observe. We can observe in our 3 independent trials that we have either 0 successes, we can have 1 success, we can have 2 successes, or we can have 3 successes. We already know that up front. So if we have 0 successes out of 3 independent trials, our prior distribution, which is now in this plot, blue, will mathematically shift with the Bayes theorem, which comes later, to this orange distribution. So the probability of actually being in the weak regime increases a lot, and also even the probabilities of the weak regime, they are moving a little bit to the lower values. If we have one success out of 3 trials, then we have same thing, but less pronounced. We now have these two modes being basically in equilibrium a little bit there. If we have 2 successes out of 3 trials, then we still think we are in the strong regime, but that confidence we have actually drops a bit, and the probability of being in the weak regime here increases. And it is only when we have 3 successes out of 3 trials that you see the probability here at the strong regime increasing and the probability of being in the weak regime actually dropping much more. So this is the pre-posterior Bayesian analysis. Before we do the test, we already update our beliefs in a mathematical way. Now, up to our utility evaluation. We said first that we are going to take the test protocol which reduces uncertainty the most. Now, how do you measure this? Well, actually, there is a metric for the uncertainty in a parameter, and this metric is the entropy. And the more negative the entropy is, the more information you have. So for all of those cases I visualized on the previous slide, I have now also evaluated the entropy. So the prior entropy for this blue curve is minus 2.78 bits. The exact number and so on, not too important, it's just a negative number. The posterior entropy of this orange curve is minus 1.49. Now this is less negative, so actually you are losing information. So if you do those 3 independent sprinkler tests and you observe 0 successes out of your 3 trials, you are now less confident about your number of your probability for your sprinkler effectiveness. And you see the same thing when you have 1 success out of 3 trials, and the same thing, but of course different numbers, when you have 2 successes out of 3 trials. So you lose confidence there. And it's only when you have 3 successes out of 3 trials that we have a positive information gain. Our posterior entropy is now more negative than our prior entropy. Now I can put these values into a table, and so we have them here. This is our information gain, the difference in entropy between the prior and the posterior. And this doesn't look very good, as in most possible test outcomes have a negative information gain, so we're not learning anything. So it seems like a problem. There's an additional point we need to consider. Actually, if we are honest about what we have set up front, our prior distributions, we actually think that we will see 3 successes. This is the probability that we think we will see. And we find it very unlikely to see 0 successes. So this is just calculating through with our prior beliefs what we actually expect to see. And then our expected information gain is the average calculated here on this basically a discrete distribution. So the information gain for each of those possible test outcomes with the weight of equal to the probability of having those test outcomes. And this is positive. So for our 3 independent sprinkler tests, we have a positive expected information gain. We did the same thing for our 100 independent fire door closure tests, and we have then information gain on our sprinkler effectiveness, really. And I refer to the proceedings for more details on that. It's just because we are now more confident of being in the strong regime. But still, if we compare these 2 cases, then still the 3 independent sprinkler tests, they have a larger expected information gain. So the preference here goes to the sprinkler test protocol. Now there are 2 things I need to now explain a little bit more because for most of you probably you're not really familiar with those concepts. One is Bayes rule, second is the concept of utility. So first, Bayes rule. What I recommend you to do, not necessarily now, but when you take a little bit of time for that, is go into YouTube, go to 3 blue 1 brown, ask for Bayes rule, and you have this visual representation of Bayes rule. Very recommendable. Here I'm just going to run you through a basic case, really. So Bayes theorem, what does it allow you to do? It allows you to evaluate the probability of a certain hypothesis you have given your evidence in a mathematical way. And how do you do that? By looking into the probability you have for your hypothesis before seeing the evidence, and taking into account the probability of seeing the evidence if your hypothesis is true. And you need to modulate this with the probability of seeing the evidence in general, both if your hypothesis is true and when it is not true. So we can look into this with an example. For example, in the room here in Ljubljana, the fire alarm goes off. Is there really a fire? So, base rule, probability of a fire given that there is an alarm. Just fill in symbols here. Is the probability of having the alarm if there is a fire, multiplied with the prior probability of having a fire, divided by the probability of having an alarm in general, both when there is actually a fire and when there's not. Background numbers. Fire detection is very good, so 98% detection probability. Probability of having a fire is very low. Daily probability, order of magnitude 2.75 10 to the power minus 5. Probability of a false alarm daily, order of magnitude 2.75 10 to the power minus 3. Here's the I rounded the numbers a little bit so that they would look very similar. Put everything together in this equation. So at the bottom here, probability of having the alarm with the fire, probability of having the alarm without the fire, filling in the numbers. Probability of not having a fire, I rounded it here to 1 because my slide is a bit too short. You get rid of the 2.75s, get rid of the 10 to the power minus 3, everything simplifies to this. The denominator is basically 1, so what you are left with is 0.98 10 to the power minus 2. So this is our probability we have if the alarm goes off right now of actually having a fire. And then this is actually very interesting to just think about for a second. Now what now happens if you spend lots of money on improving your detection probability and having, for example, a probability of having an alarm given a fire of 1. Well, this doesn't change this number immediately. This number is very much governed by the probability of having false alarms. If you have a continuous distribution, as we have in the example I showed earlier, same thing. And for the derivation, I again refer to the proceedings. Now up to utility. So this is quantification of what we actually want to improve by doing the test. I gave 3 standard things we might want to improve. We might want to reduce uncertainty. We might be interested in money, basically, or we might want to have an environmental benefit of doing the test. For each of these, you can specify metrics. The most common one, and what I'm going to go into a little bit more, is the economic metric, which we denote with value of information. So this is a dollar value, a euro value, or any currency you are interested in, which denotes how much it is worth to have the extra information you get from doing the test. Of course, doing tests also costs money, so you can take this into account as well, and then deduct the cost of doing the test from your value of information, and then you get a net value of information. Small example, one I presented here in Ljubljana 2 years ago. Post-fire assessment of a concrete structure. There is a cost structure. I'm not going to go into any specifics here now. And then before doing any test, we have an expected cost of 40% of our repair cost. Okay, if we do a hammer test, our expected cost, so before doing the test, is only 11% of our repair cost. So we do a hammer test and our expected cost reduces because our information now is better. If we do a collar test, our expected cost reduces to 15% of our repair cost. So what does that mean in terms of value of information? Well, this hammer test has a value of information of 29% of our repair cost, which is the cost we would have without doing the test minus the cost we still have after doing the test. So our expected reduction in cost is 0.29 CR, and that is the value of information. You can then also take into account the cost of actually doing the test, which brings us to our net value of information. And so with basic assumptions and the results which are included on the slide, we can rank our options, our test protocols, in function of their net value of information. They're all positive, and the largest positive value is for our hammer test. So different conference, different presentation for all of the details, but the concept here is very clear. From an economic perspective, yes, you should do a test, and you should do the hammer test and not the color test. And I'll end now with a second demonstration, and this is a demonstration on the PMMA case I referred to earlier. So we're looking at the time to ignition for PMMA plate, and the test setup is actually very, very clear. We have an exposure of 20 kilowatts per square meter and so on. And what we want to do is we want to reduce uncertainty on the time to ignition as far as reasonably practical, whatever that means in this specific case. So we want to know how many tests should we specify, or at least we want to have some input on deciding on how many tests we want to specify upfront. So what does that give us? Our goal is reducing uncertainty, so we're going to again talk about entropy later on. Our experimental protocols, they are very clearly defined. The only thing we don't know is how many repeat tests we're going to do. So how many trials will we have? Is it just one? Will we do 3, 5, 7, or maybe even 30? We then think about how this time to ignition is actually characterized. We say, well, the time to ignition of a specific batch of material is probably something like a normal distribution with a mean value and a standard deviation, which we are not sure of what this mean value and the standard deviation would be. So our uncertain parameters are this mean value and this standard deviation, uncertain parameter of interest. And we're going to run this through our calculation by first defining our prior distributions based on the information we have. The information we have is a simple model from Drysdale, which links the ignition temperature to the time to ignition. And for the ignition temperature, we have a range specified by Babrauskas. So we limited, we can look into this more, but it's sufficient for now to make our first evaluation. With that in mind, we specify uniform distributions for our mean time to ignition and a uniform distribution for our standard deviation for the time to ignition. And I'll have references later on which give more details on how this is specifically done. These are basically assumptions up front because we don't have more clear information on this mean or on the standard deviation. So what we're going to do a sanity check. Should always do it, basically. And we're going to run these priors through our model here. So we're going to sample mean values, we're going to sample standard deviations, and with those we're going to sample time to ignition realizations, and we plot here a histogram for this time to ignition, which is just, again, honesty, really. It is just if you believe this, this, and this, then what you actually believe on your time to ignition is this histogram here. And looking at it, we then say, okay, this is reasonable. We're going to proceed with this these models. Then our pre-posterior Bayesian analysis, Bayesian updating. If you take here example of 3 trials with a specific 3 realizations for our time to ignition we get from our experiment. So these are hypothetical observations. This updates our time to ignition distribution a bit. It has quite an effect on our beliefs on our standard deviation. So it's moving very much to larger values. And you see that our mean value moves or updates from this uniform prior to something which is much more bell-shaped. If you have 30 trials, and these blue dots are 30 realizations, then you have the update as you see here. So the darker one is the updated time to ignition, with here a much more clear value distribution for our standard deviation and a much more clear distribution on our mean time to ignition. Now these blue indications, they are possible realizations when you do 3 trials or possible realizations when you do 30 trials. Now there are of course many possible realizations, right? So you need to repeat this. Is what you see here. For 3 trials, you just sample 3 3 realizations, sample 3 other realizations, and so on, and so on, and so on. And for each of them, you get yourself an updated distribution. That means also that for each of them, with each updated distribution, you have an information gain value. And so this is what you then have here. So we're now in the utility evaluation for each possible set of realizations on our experimental protocol. We have an information gain. We plot this information gain here in a histogram, and the dashed line is the average of the histogram. So for one trial, this is a very narrow distribution, and then as the number of trials increases, this distribution shifts, and the expected value, the average value, also goes a bit to the right. But what you already observe here, maybe not too clear to see, is that in the beginning the histogram changes a lot, but then later on, if you increase the number of trials more and more and more, the histogram doesn't really change that much anymore. And we can really see this if we plot the results in a different fashion. And that's what you have here. So exactly the same information as we have here is now in this plot. So instead of having histograms, we now have box plots. And instead of having a dashed line, we have a full line with the average value. And you see that the average value, so this expected information gain, it increases with the number of trials, but then at 7 to 10 trials, it actually flattens out. So we believe upfront, if we are honest about what we actually believe, that it makes little sense, or at least it doesn't seem very efficient, to just go immediately for 20 or even 30 repeat trials. 10 repeat trials will give us a very good evaluation of our information gain, and 7 might actually be very good as well. And we have validated this with a data set by David Morissette. So there actually 100 trials were done with exactly this case of PMMA and 20 kilowatt per square meter and so on exposure. And you see that the information gain, which was observed by David Morissette, actually flattens out completely above 7 trials. With that, I'm at the end of my presentation. A full write-up of different cases I've presented here today is hopefully going to be published soon. The reference or wishing reference is here listed on the slide. For project updates and so on, I refer you to our team site. And in conclusion of what I've presented, well, if you need to decide on which test to do or whether to do any tests at all, you don't need to just follow your gut feeling or some subjective statements. If you are just willing to do a little bit of mathematics and be honest about what you know and what you don't know and what you believe about the models and so on, you can actually make an explicit evaluation. And you can then be very clear about which test protocol you should do. With that, thank you for your attention, and you can always reach out to us if you have any questions. Thank you.